Okay, so if you haven't watched the YouTube video on nuclear decay, you really need to, but let me try to give you the Cliff Notes version real quick here. Back in the early 20th century, physicists were working on the quantum stuff, and we've spent quite a bit of time talking about that. The idea that particles are not indivisible. Right? John Dalton had this theory that particles were basically an atom is as small as you can make something. And if you try to cut it in half, not possible. And all of a sudden, around the turn of the century, 1900, give or take, and all of a sudden new scientific evidence suggests, really two things. One, that there are subatomic particles. There are protons, neutrons, and electrons, and that changes everything. Two, the other really weird thing is that although scientists thought beforehand you couldn't cut an atom in half, they had this theory that energy could be any value of energy, and all of a sudden they have evidence now that energy actually is discrete. And those two things are almost opposites. I just want to make sure that that's kind of clear in your heads. They used to think that atoms were discrete particles that you couldn't cut in half, and they used to think that energy was on a continuum and that any energy values were possible. And evidence now seems to indicate otherwise. Matter itself seems to actually always be divisible into smaller and smaller and smaller chunks. Tomorrow's lesson is going to be on quarks, which is basically the idea that once you get from the atom level down to the subatomic level below that, we just seem to be getting smaller and smaller and smaller. So that's for matter. And yet for energy, Planck discovered that energy seems to be quantized, where it only comes in certain specific packets of energy. And so for those of you guys who are doing calculus, this is kind of like that limit concept, is there are certain things that you can keep getting closer and closer and closer to zero. And there are other things where it's like, no, this is as small as something ever gets. You know how like a cell is the smallest functioning thing of life in biology? Well, it's kind of like that for quantized energy. You can't have anything smaller than Planck's constant. Okay. So anyways, those things are coming together at the turn of the 20th century, and physicists are realizing that there is a whole realm out there, the quantum realm, that they've never really discovered. At the same time, though, they've started to discover that there is nuclear energy inside of atoms. And if you watch the YouTube video, you would have hopefully learned a little bit about Einstein's famous equation, E equals mc squared. So I'm just going to do a quick little recap before we move on. But at some point, hopefully you've watched my video and I've talked about E equals mc squared. So here's basically the concept. Scientists are now realizing that these subatomic particles exist. Rutherford in 1909 hypothesizes that they're in a nucleus. And if you were to draw a nucleus, it might look something like this, where you've got all of these protons and neutrons stuck together in a nucleus. And Rutherford's model originally probably looked something like this, where electrons were orbiting around the outside. I don't care about the electrons right now though. I want to focus on that nucleus. The nucleus made not a lot of sense from a electrostatics point of view, though. Because if you were to zoom in on the nucleus, you have a whole bunch of positives right next to each other. Do positive ions like to be next to each other? No, not at all. Not in the slightest. And this was a little bit perplexing in 1909, because why would all of these positive protons be so tightly compacted next to each other? And one of the things I did in the YouTube video for a practice was to see whether or not the force of gravity could actually be stronger than the electrostatic force that would be wanting all of these positive protons to basically repel each other. And scientists discovered that no, the force of gravity is actually quite weak. We think of gravity as being strong because we see the effects of it on a macroscopic scale. But truthfully, two individual particles, gravity between them is actually very, very small. So scientists suggested two new forces. One is known as the strong nuclear force, and one is known as the weak nuclear force. The strong nuclear force basically explains that it's scientists' way of trying to explain why all of these positive charges stay next to each other. That there must be some sort of glue keeping them together. And that is known as the energy found in the E equals mc squared formula. So there must be some sort of energy inside here keeping all of these positive charges next to each other. And it was known as a mass defect. When scientists measured the masses of nuclei before and afterwards, they discovered that masses didn't add up. And this makes no intuitive sense. You would think that if you add up the mass before and you add up the mass after, according to every chemistry equation you've ever learned, there's a law of conservation of mass. Einstein suggested there's actually a law of conservation of mass energy, where mass can actually be turned into energy, and the energy can be used to glue things together. And so there's actually extra mass hidden inside this nucleus, which is like the glue that's inside there, keeping them together. Sometimes when I explain this, I try to explain it like when my daughters are playing with Lego. So imagine my daughters have a whole bunch of different Lego pieces, and on their own, they weigh a certain amount. And yet when you put them together, somehow it weighs more. And it doesn't really make sense as to why it would weigh more when they're together, but that extra mass is in the form of energy. And then when they separate, all of a sudden then there's missing mass, and that missing mass is in the form of energy. And that's what we're going to talk about today, is that as scientists were then discovering that mass could be converted into energy, they were able to basically create nuclear technology. And I need to preface this by saying, guys, I'm a physics teacher in high school. I am not a weapons-grade nuclear physicist, so I don't really know what I'm talking about other than the basics. But that's all you really need here, is just like the basic concept about how today we're going to talk about fission and fusion. The concept of how, as nuclei are either forced together or removed apart, how there is a massive amount of energy tied up in this nucleus. Okay. One more thought, and then I'll get to the notes here. The weak nuclear force, by the way, is radioactive decay, which you should have learned of 3 types of decay. There's alpha, beta, and gamma decay, and that's basically where a nucleus becomes so unstable that of all of these positives that are stuck inside here, a few of them decide to like take off. And if 2 protons and 2 neutrons take off, which I guess we normally write like this, it's called an alpha particle. That's alpha decay. If an electron takes off, that's known as beta negative decay. There's also something known as beta positive decay. And so as this nucleus can slowly but surely break apart through the process of decay, that would be your weak nuclear force at work. So anyways, that's the Cliff Notes version. Let's talk fission and fusion. I'm going to finish my lesson talking about the geopolitical implications, but let's talk about them to begin with right now. You guys have done some social studies, I'm guessing, right? Everyone's taken some social studies, and you learned about the 1930s. In the 1930s, the world was in a rough place. 1929 was the collapse of the stock market. You guys heard about that at some point in social studies class? And the 30s were the Great Depression. And worldwide, the United States, Germany, all of these countries were trying to figure out how to get their economies back on track. And in the mid-1930s, Adolf Hitler rises to power and begins basically his conquest, his retribution tour in Europe, right? And a lot of famous German scientists, who we don't actually have their names in here, but some German scientists were beginning to work on nuclear technology. And there's a very famous letter that was written. It wasn't written by Einstein, but it was signed by him. And Einstein signed this letter addressed to FDR, Franklin Delano Roosevelt, President of the U.S. It was in 1939, which is basically the year the First World War started. And basically it was a letter saying, you need to start working on atomic stuff now, because German physicists have figured out or are about to figure out how to split and fuse atoms, and they're going to make weapons of mass destruction. And so FDR, U.S., get on it. That's basically the point of the letter. And the history basically is that FDR kind of was like, nah, we'll be fine. Because if you guys know much about World War II, the United States didn't join World War II. You guys remember when they joined World War II, what it was that kicked that off? Yeah, Pearl Harbor, right? December 7th, 1941, I think it is. And so it wasn't until a couple years later that FDR started to finally take that seriously and go, okay, yeah, we really can't kind of live on the other side of the Atlantic Ocean and just pretend that war is just in Europe, because as soon as that war came to the U.S., all of a sudden they were all in, right? And so the project was called the Manhattan Project. And a famous scientist named Enrico Fermi was basically working on trying to control nuclear reactions. Physicists had found a way to create nuclear reactions. That wasn't the problem. But we're going to talk about it in our notes here. They could undergo like a meltdown. You ever heard that phrase before, where like a meltdown occurs? If you can't actually control your nuclear reactions, you're going to blow yourself up before you can blow up your enemies. And so they spent years trying to basically perfect the bomb, right? And they did a lot of testing in the South Pacific, in the New Mexico desert. And by the time the year 1945 came around, once the Allies had finally sort of pushed back Germany over on the European front, the U.S. decided to drop 2 bombs on Hiroshima and Nagasaki in Japan to end the war. And really the implications of those two bomb droppings still resonate to this day, where, I mean, even right now, Donald Trump as US president is dealing with Iran, dealing with North Korea in terms of trying to figure out how nuclear technology is possibly going to be used again in the future. So I find this lesson fascinating because it's not just about the physics behind it, but there is a lot of societal and a lot of social studies implications that go along with this. So you don't need to memorize the social studies part of this, though. I do not expect at all you to be assessed on that. But you do need to know a little bit about the physics behind this. So, okay, let me start now then. There are then two main types of atomic physics nuclear reactions we know of. One is called fission, one is called fusion. You guys good? So fission is very similar to radioactive decay in that it involves things that are breaking apart. They're going to split. The big difference, though, is radioactive decay involves a large particle. Fellas, can you? Radioactive decay involves a large particle spitting out and emitting a small particle. An alpha particle or a beta particle are usually the main ones. In fission, it splits into multiple smaller nuclei, and usually these things are still relatively large in size. There are many known fission and fusion reactions, most of which we can't harness very well on Earth, but there are many different types. And as long as those smaller nuclei, as long as they have a difference in mass, which is in the positive direction, it releases energy. The release of energy is due to a loss of mass, the mass being the binding energy in the formula E equals mc squared. Okay. Now, fission reactions are the main ones that were being worked on in the 1940s, and many nuclear reactors around the world to this day still involve fission. One of the downsides to fission, though, is that it usually leaves a lot of nuclear waste. If you guys have heard of Chernobyl, the meltdown that happened at Chernobyl has made it so that that location is still basically uninhabitable. Fusion would be a much better option. Unfortunately, fusion has not been perfected yet in terms of trying to make a power plant out of it. It involves taking smaller nuclei and trying to stick them together. It's actually what makes our sun work. The downside to it is that it actually requires a huge amount of activation energy. For any of you who've learned about that in Chemistry 30, in order to make a reaction run, all reactions require, if you've kind of seen this diagram before, they require a little bit of energy to kind of get over the hill, so to speak. And then once you get past that barrier, then energy can be released. From a physics point of view, if you know what I mean by activation energy in a chemistry sense, the activation energy in physics is the ability to take some protons and actually bring them together. Do these three protons want to come together? No. But if you can get them to come together, that activation energy, once that barrier is achieved, you'll actually get back a ton of energy. Question? Yeah, I mean, what ends up happening is the missing energy becomes that glue, or that glue becomes the missing energy. Does that make sense? So like you will need some energy here in order to put them together. What ends up happening though is that the mass that's found inside will be less. So like these three particles right here will actually have more mass than when you actually bring them all together. And so therefore when there's more mass here and somehow there's less mass here, that less mass is the loss of energy. Does that make sense? So it's a very, very strange concept. It does not make intuitive sense as to why mass would be quote unquote missing. But yeah, that missing mass is the energy that's the, you guys have maybe learned of like a delta H before in chemistry. That missing mass is effectively your delta H. Our sun is driven by a fusion reaction. Our sun requires 10 million kelvins of activation energy to occur, which explains why fusion isn't very practical on Earth, because 10 million Kelvin is not a reasonable temperature for most power plants to have. Later I'm going to talk about cold fusion, which is the idea of trying to make this fusion happen, but at a much lower temperature. Okay, you are expected to know a couple of basic reaction equations. I don't think you necessarily need to memorize them, but you should definitely be familiar with the basics behind them. There are two common fission reactions. There are many more, but these are the most common two, and it usually involves uranium. Going back historically, uranium was actually the main source of fissionable material that was being used back in the 1930s, 1940s. I was researching it last night to make sure I can remember. Canada was actually meant to be one of the United States' main source of uranium because Canada actually has some uranium deposits. The Belgian Congo was another place. And what ended up happening back in the 1930s, which then started Einstein's letter to FDR, is that it was being discovered that German physicists were starting to stockpile uranium. They didn't know how to use it yet, but they knew they needed uranium. And so that was kind of the tip-off that was like, hey, these guys over here, they're mining uranium here and here and here. And uranium could make a bomb. We better get on this too. Does that make sense? One more kind of cool thing that I didn't realize until I researched it last night. FDR, Roosevelt, he was the president during most of the start of the World War. Truman was the president in 1945 when they dropped the bomb. Truman did not even know that the Manhattan Project was in existence. It was such a secret hush-hush that very few people even knew about it. And so the next president of the United States, when he was elected, or I don't remember how that happened, but when Truman basically became in charge, he didn't even know that they were working on nuclear materials. It was that much of a secret because it was really like an under-the-radar sort of thing. The Germans didn't want the Americans to know. The Americans didn't want the Germans to know. Anyways, okay, I'm getting off topic. Uranium, then, is one of the most common fissionable materials. And one of the most common isotopes is uranium-235. Well, actually, no, I take that back. The most common isotope of uranium is actually uranium-238. That is the most common one. The problem is uranium-238 is stable. And if I were to use the word stable, what that means is that all of those 238 particles stuck inside the nucleus, they actually can stick together. And they don't really have a half-life. But uranium-235 is not as stable, especially if you can find a way to add one neutron. And this is what makes fissionable reactions so cool. Uranium-235, if you can find a way to add one neutron to it, pops up to uranium-236. And this is highly unstable. It actually breaks apart. And so if you can imagine that you had 236 Lego pieces together, and all of a sudden, it's too many. All of a sudden, it can't handle it anymore. It's going to split into two pieces. They're not equal pieces, but the two most common orientations are it breaks up into barium and krypton, or it can break up into xenon and strontium. And then what ends up happening is not only will it break up into two unique nuclei, but it'll also create more neutrons, which is where the phrase chain reaction comes from. Because what ends up happening is one molecule of uranium bumps up with a neutron to become this uranium-236, and then it splits into two pieces. But let's say that it didn't make extra neutrons. Then it would just stop. And you would release one unit of energy based on breaking up one molecule of uranium. But can you kind of see how if it produces more neutrons through your product, then these three extra neutrons can then be used to hit more uranium and break up more. And I've got a picture here to try to illustrate it. This one right here I think is the best one to kind of illustrate the concept. Here's some uranium-235. A neutron comes in, adds to its nucleus, and it now becomes unstable. The forces that are internally within the nucleus become too much to withstand all of that electrostatic repulsion, and it splits into two pieces. Piece one goes this way, piece two goes this way. But the cool thing is it spits off three more neutrons. Well, those three neutrons can be used to hit other examples of uranium-235. And this guy right here spits off its three neutrons, and hence the phrase chain reaction. I actually have another example of it going on right here. You can see reaction one. Uranium picks up the neutron, turns into 236. It breaks into two pieces. I don't actually care what those two pieces are. Sometimes it splits up into barium and krypton. Sometimes it splits up into xenon and strontium. It really doesn't matter. We don't really care which one it is. It does some of both. Sometimes it gives off three neutrons. Sometimes it gives off two neutrons. Based on that, on average, it gives off 2.5 neutrons. And so sometimes you'll see it written like this. It gives off an average of 2.5 neutrons. Well, then some of those neutrons create the next reaction, which make more, which creates the next reaction, which creates more. Does that make sense? This is what was the challenging thing for physicists then back in the 1930s, 1940s, is now that we get a nuclear reaction going, how do we control it? I would say that there's two main places that we use nuclear technology. One is unfortunately for weapons. Now, when you're trying to make a nuclear weapon, you don't overly care about controlling the weapon once it gets going because the whole point of the weapon is to blow up your enemy, right? And so if you lose control of a nuclear weapon, as long as it's not in your backyard, you're good. And so the real challenge was, how do we make the nuclear weapon only explode when we want it to and not explode, while it's in our possession, right? But once you get the reaction going, by sending a single neutron into uranium-92, once you get it going, feel free, let the reaction take off. But the other common source of nuclear technology is to make a power plant out of it. And that's where meltdowns happen. There's one really famous meltdown in Chernobyl. You probably heard of that one. There was also a meltdown 5 years ago, give or take, in Japan. Anybody ever hear of that one? There was a tsunami that caused some technical issues, and they had to use, fortunately, a lot of ocean water to try to cool it down and prevent the meltdown from happening. But there was a pretty almost catastrophic one in Japan recently. And that's really what's going on, is that this statement right here. Each reaction leads to more reactions. So, does that make sense, the idea here that one reaction will then self-perpetuate the rest? So, what you may need to know then, and we're getting to the obscure stuff. We're almost to the point where I highly doubt this will be on the diploma. But it's still in the curriculum, so I'm going to try to teach it as best I can. All nuclear reactors then need what's known as a moderator. And the moderator's job is to slow down your neutrons. Because if a fissionable reaction releases more and more neutrons, if the neutrons get spiraling out of control, you get that meltdown. So the moderator's job is to try to slow down your neutrons, basically. Okay. One of the most common things they use for reactors then is something known as a control rod. And what they do is they dip the control rods into the core of the reactor, and those control rods will either absorb neutrons, or if you remove the control rods out of the core, then they won't absorb neutrons and the reaction can proceed faster. So I don't know, it's like a brake, so to speak, right? If you put the control rods deeper into the reaction core, the cadmium will absorb some neutrons and basically it'll stop your reaction, right? Because the reaction requires neutrons to get going, right? So steal all the neutrons, you're good. Pull the rods back out and it speeds it back up. However, there's one more problem. The neutrons that are emitted travel way too fast. Okay. One of the questions that you're likely to be asked, and I gave you some practice ones on your practice assignments, but when you kind of consider how a nuclear reaction takes place, you have a nucleus that would have looked something like this. And it's now going to split apart, right? And so something's going to go this way, something's going to go this way, something's going to go this way, mostly according to the law of conservation of momentum. Does that make sense? You have an explosion taking place, right? Where one of your things, like say the krypton part, could go this way. The barium part could go this way, and your 3 neutrons could go this way. In terms of how much momentum they take with them, because the neutrons are the smallest by far, they take most of the velocity. Does that make sense? Krypton and barium, comparatively, rather large. These 3 neutrons, rather small. So when the explosion takes place, momentum has to be conserved. The smallest particles get the highest velocities. And so based on that, where was I here? Based on that, these neutrons are traveling quite quickly. And so it's sometimes very challenging to slow them down. We don't necessarily want to have too many of them, and we don't want them traveling too fast. So the problem to take care of too many is the control rods with cadmium. Okay? If you have too many neutrons being released and you want to stop your reaction, use the control rods. But the other problem is they're traveling really quick, and they might miss the nuclei or hit it with too much energy. So what they need to do is they also need to slow them down. And the way they slow down these things is using hydrogen atoms in water. Okay. So a bit of a chemistry lesson for those of you who aren't familiar with this. Water is a bent molecule in this shape right here. HOH looks something like this. And chances are the way it's going to work is that these hydrogens right here, they are probably just a single proton. And the reason we know that is because water is a very polar molecule. There's lone pairs of electrons over here. And this leads to water's polar shape. And so these hydrogens are basically a single proton. And if I were to consider these hydrogens from like a describing them with atomic notation, it's probably 1, 1 hydrogen, where there's 1 for the atomic number, 1 for the mass number, there's a single proton. But these hydrogens right here, they have the capacity to pick up extra neutrons and become 2/1 hydrogen, or possibly 3/1 hydrogen. Those are other isotopes of hydrogen that we know of, where this one right here is 1 proton and 0 neutrons. This would be 1 proton and 1 neutron, and this would be 1 proton and 2 neutrons. And so water is a very cheap, plentiful supply of protons, and these protons can very much absorb and slow down neutrons when they're traveling too fast. So that's basically what I mentioned right here, is that you can try to create hydrogen 2 out of it, and it makes what they call heavy water. The reason why they call it heavy water is that the water now has probably 2 extra neutrons, 1 for each of the 2 hydrogens, and this has now prevented the neutrons from continuing their process, and it sort of slows them down or stops them, almost in a similar way to how the cadmium works. The problem then is how do we find a way to moderate this and control the reaction? And so again, I'm not a nuclear physicist, I don't know all the details, but here's a couple of ways that different countries use their nuclear reactors to try to find a way to slow down their neutrons and prevent them from going too quick. One is, in America, they used enriched uranium. Typical Americans. Sorry if anyone is American here, but like sometimes Americans are very like, yeah, bigger, better, right? And so if you could use 50% pure uranium, why not use 60% pure uranium or 99% pure uranium? And when I say pure, what I mean is that much uranium is in the 238 isotope range. The very, very few amounts of uranium are in the 235 range. And so if you're going to have, like, say, 95% 238 and 5% 235, that would be a pretty common breakdown in your uranium. So this would be unenriched uranium. Well, Americans, they typically like to try to change the perspective and make it, well, let's only use 5% 238, 95% 235, and let's just use more of this stuff. So that's one of the things they use in their reactors. And because they use extra uranium-235, they find a way to slow down the reaction using water, but they used an enriched amount of uranium. So that's one of the unique twists that Americans have. This is kind of cool. There are actually nuclear reactors in Canada. They're known as CANDU reactors. It stands for Canadian Deuterium Uranium. And what we end up doing is we actually use heavy water as our moderator. And so rather than using regular water and using regular water to steal some of the neutrons, we use water that's already considered to be heavy. And so therefore the water molecules have already absorbed neutrons. What the water then does is slows down neutron flow, but it doesn't actually steal them and absorb them. So remember how we have to have those rods that get dipped down into the reactor core to steal neutrons? Water can be used to basically steal neutrons. But you can also use water to slow down the neutrons if the water is already heavy, because the heavy water can't steal the neutrons, it can just slow them. And so that's what ends up happening in Canada reactors. CANDU. Canadian Deuterium Uranium. Deuterium referring to the common name for hydrogen 2/1. That's known as deuterium. 3/1, by the way, is known as tritium. Yeah. The final one is that in Russia or the United Kingdom, they often use graphite rods, which is more or less what I was describing up here, only graphite is carbon. And so they use rods like boron and cadmium, only they use graphite, and it's supposed to help slow down reactions as well. The problem is, graphite is carbon is combustible, and if you ever accidentally add in oxygen, carbon plus oxygen goes kaboom, which is what actually happened in Chernobyl. And so you'd like to try to avoid that. So you have to basically have a completely controlled environment so that there's no oxygen getting inside. Okay, most of what I've taught you up till now is really just background information. I highly doubt you will be assessed on that. This is something that you will likely be assessed on. You might be asked to calculate how much energy could be released by this sort of reaction. Now, I need to preface this by saying you would never be given a question like this without a chart. Okay? If they were to give you a nuclear reaction and say, tell me how much energy would be released, they would have to give you a chart which would involve masses of individual components. Because what you're going to do is you're going to find the mass of this side right here. You're going to find the mass of this side right here. And you're going to discover that the masses are not the same on both sides, which breaks every rule you've ever learned in chemistry. Because in chemistry, you're supposed to have a law of conservation of mass. What we're going to discover is that the masses between these two sides will be different, and there will be a loss of mass, and that loss of mass will be the energy found according to the equation E equals mc squared. So if anybody has notes printed off from previous examples, I gave you a slide that has a whole bunch of masses found in them. I noticed some people grab their periodic tables. The masses on your periodic tables will not be helpful because those are molar masses. And so those are the masses when you have a mole worth of substance. We literally talk about the mass of one individual particle or proton. And so this was a slide that was in our last set of notes that if you're given a question on a diploma like this, they would have to give you a chart, probably not the whole chart, but they'd have to give you a small portion of the chart where they tell you what the mass of each individual particle happens to be. So I've got it on a slide right here. We're just going to have to go back and forth and just try to transfer the information here. So one of the things we're going to require is the mass of uranium-235. And if you can find that on this chart right here, uranium-235, okay, I need to write this down because we want to be precise here. Uranium-235 is 235.043930. That's uranium-235. I'll write this on the slide in a bit. We also require the mass of a neutron. And I put the neutron masses kind of sideways on here. A single neutron has a mass of, where is it? Neutron is the bottom one. 1.008665. We're also going to need barium-141. Barium-141 is 140.914412. And krypton 92. Okay, so that's 91.926156. Okay, that information would have to be given to you. Is that clear? Like, that is not common information. So I'm now going to write all of these numbers down up here, and we're going to find the total mass before the total mass afterwards, and we're going to discover that there is missing mass. So let's try this. This right here is, let's try this. We need 235.043930, and I'm going to need to add to it one neutron. So that'll be 1.008665. So that'll be my reactants mass. So I have a reactant mass of 236.052595. And then for the products, when I add it up, hopefully this works, we're going to have 140.914412. We're going to have 91.926156. And we're going to need to have 3 neutrons. So 3 times 1.008665. Okay, so I've got a final mass of 235.866563. Is anybody else doing this along with me? Did you get the same thing as me? Okay. This makes no intuitive sense to me, right? And this is where at the quantum level, at the microscopic level, you're somehow telling me that like when you add all the masses beforehand and you add the masses afterwards, they somehow didn't equal each other, right? And like when I think of mass on a macroscopic level where I think, well, there's a certain number of particles. These particles are supposed to weigh a certain amount, right? And when we think of it from a chemistry point of view, carbon should always weigh what carbon weighs, and boron should weigh what boron weighs, right? But when we actually add these up and they change and they transmutate between different elements, apparently mass was lost. The reason why it was lost is that energy was needed to bind all of these 235 particles that were stuck inside of uranium. It was heavier because there was mass stored in the form of energy, and that energy was helping to glue it all together. Right? So, you guys ever watch the first Lego movie? You know, the one where like the dad is like in a crazy glue all the Lego bricks together at the end of it? You ever seen that movie? That's the analogy I think of in my mind, where all of these Lego bricks, these 235 Lego bricks, they were glued together by crazy glue. And that extra little bit of mass inside of there explains why this is a little bit higher than this one, because you needed a little extra crazy glue to glue them all together. As soon as you take them apart, there's now a missing mass. So all you're going to do is subtract these two numbers. So that's your next step. 236.052595, subtract your answer. And I've got a missing mass of 0.186032. Now, this is where you got to be really careful. There are two common units for mass. One is the kilogram, and one is the atomic mass unit. You might ask, Chris, why do we have two different units? I think it's very similar to why we have electron volts and joules. Kilograms is a great way of measuring large amounts of mass. But when you're talking tiny amounts of mass, measuring things in kilograms is kind of ridiculous. So that's why the unit atomic mass unit, which is represented by the letter U, was developed, is that this is how many atomic mass units there are. We need to convert that into kilograms. And so the conversion is that there is 1.66 times 10 to the minus 27. That's how many kilograms there are in an atomic mass unit. And that is on your data sheet. And if you watched my YouTube video from the previous one, I should have talked about that, I hope. So you have to make sure you use kilograms. In previous diploma questions I've seen, sometimes they give this chart in atomic mass units. Sometimes they save you a step and just put it in kilograms in the first place. Okay. Long story short, though, find that missing mass, convert it to mass in kilograms. So times by 1.66 times 10 to the minus 27. I have a missing mass of 3.08, etc., to the minus 28. The name we give for this is called the mass defect. The missing mass. The glue that used to be required to hold them together is no longer needed. And so it gets released in the form of energy. You now use the formula E equals mc squared, and you use this mass. So take that mass, times by the speed of light squared. And I've calculated an energy of 2.779 times 10 to the minus 11 joules. Now, I probably would have talked about this in my YouTube video. I want to discuss this number a little bit. You might think, Chris, that's not a lot of energy. To the minus 11 joules? Why is that so small? Because it's for one atom of uranium being broken apart. Are you only going to use one atom of uranium? Highly unlikely. Let's say that you used a mole's worth of uranium. You guys know how a mole is 6.02 times 10 to the 23? Imagine that you used a mole of uranium. If you were to times this by Avogadro's number, well, now you're going to get a lot of energy just from using a mole, right? So the amount of energy you're going to get is likely going to be very, very small. Okay. Chances are you're actually not going to be asked to calculate it in joules. You're going to be asked to convert it into electron volts, which means you may have to then divide or multiply by 1.6 times 10 to the minus 19. But again, this is the amount of energy you get for one atom of uranium that's splitting apart. Can you replicate this process? It's not overly hard. Take a chart of data that you're given, add up the before and after, find the difference. They will not be the same as each other. The missing mass is your glue. Throw it into E equals mc squared and just recognize that that's in joules. So if you have to make a conversion, make a conversion. Sound good? Did those of you who did the math, did you guys get what I got here? Did everybody get the value there? Okay. Okay. Fusion, I want to spend a few minutes discussing as well. Fusion is something that physicists have been able to figure out how to do on Earth, but only in bomb capacity. There have been H-bombs, hydrogen bombs. They are more destructive than uranium or plutonium, by the way. Plutonium is the other fissionable material that's often used. Fusion has been able to be discovered how to use it in a bomb, but the problem is it's been very challenging to figure out how to harness the power of fusion because it has such a high activation energy. It requires so much temperature to make fusion occur. It's supposed to be 10 million Kelvin. What is that? 1, 2, 3, 4. Yeah, there it is. 10 million Kelvin is usually the activation energy barrier required to make it so that proton 1 and proton 2 can actually get so close to each other that they can actually occur. If you'd like to research it, there's some really cool information on something called quantum tunneling. I don't think I can fully explain it, but I'll do my best. Do you guys remember the formula how E is equal to KQ over R squared? This would be the amount of electrostatic field that's being given off. We can also use the formula Fe equals KQ1 Q2 over R squared. These are some formulas we've learned. This is the electrostatic force that needs to be overcome. In order to make proton 1 and proton 2 come towards each other, they have to get incredibly close to each other. Incredibly close. And their charges are, well, their charges are 1.6 times 10 to the minus 19, right? And so to make these things come together, it requires a high amount of force. That force will then come from energy. That energy will come from temperature. Long story short, you need to superheat these things and make them slam at each other with a ton of energy to make them come towards each other. Okay? There's a cool concept called quantum tunneling that explains how they're able to do that at the subatomic level. Long story short, what you can sometimes do is take 4 hydrogen nuclei, which is what our sun does, and you take hydrogen 1, 1, and you take 4 of them. And by the time you're done, you're then able to make it into a 4, and in theory it would be like a 4, 4, but what ends up happening is it actually makes 4, 2, because I believe some neutrons are given off, or no, actually it becomes 2. It becomes 2 heliums. 4 hydrogens out of 1, 1 becomes 2 heliums out of 4, 2, or out of 2, 2. There's some equations I'm going to show you in a bit. But like I said, it takes a lot of energy. It requires a huge amount of energy to kind of make this work. Ideally, cold fusion would be the Nobel Prize winning achievement if it's ever discovered. Because if scientists could figure out how to make energy from hydrogen and helium at a low temperature, all of the world's energy supply would be taken care of overnight. Like, we're talking science fiction movies here. But it'd be cool if that could ever happen. So, let me show you some equations about fusion. This is actually what's happening in our sun. It's not actually one step, it's many steps. And so if you want to kind of follow along, what happens is 2 hydrogens fuse to form a hydrogen, which is now a 2-1 hydrogen, and this particle right here. What is this particle right here? A beta positive particle, yeah. If you watch the previous YouTube video, this is a positive electron. Yeah, it's basically a proton with the mass of an electron. Plus, it gives off this particle right here, which is a neutrino. So it's quite a complicated process. You do not have to memorize this by any means. You just need to know the basics of it. So hydrogen forms a new form of hydrogen. It forms deuterium. Then deuterium reacts with more hydrogen to form some helium. Then the helium will then react to form a new helium plus some hydrogen, which is good, by the way, because this hydrogen cycles back to the beginning. Then your beta positive turns into a beta negative, uses a beta negative to form some gamma radiation. And by the time you're done, it forms this net reaction. For those of you who've done chemistry, this is basically Hess's law, where you would then consider everything on the right-hand side, everything on the left-hand side, and kind of cancel stuff. So through the process of Hess's law, this is how much energy. It's a mega electron volt, but that's actually a considerable amount of energy. And what ends up happening, long story short, is that helium turns into hydrogen. Okay? Don't memorize the equation, just know that's the process. Helium becomes hydrogen. And in the process, a ton of energy is given off. This example right here is what scientists on Earth would like to try to do. They would like to take deuterium, which is hydrogen 2-1, add it to tritium, which is hydrogen 3-1, and if you add the two of them together, just basic math means that you'd end up with a 5-2. 5-2 would be helium, because 2 is helium on the bottom. What would then in theory happen is 5-2 helium is very unstable, and so what would happen is a neutron would get spit out. A neutron would be a 1-0, so you basically drop this from 5 back down to 4, and you'd make helium. And this would be one of the safest in terms of byproducts you could possibly have, because helium's relatively safe. Neutrons are fine. So this would be awesome if we could do it. The problem is that in order to merge these particular ones on Earth, it requires a huge activation energy. This reaction right here, we would never want to do on Earth. Why would we never want to do this reaction on Earth? What is a byproduct of this that would be catastrophic to us? Yep, that's what this is right here. Right? That's gamma right there. This was a beta positive. This was a neutrino. This is a neutrino. But this right here is a symbol for gamma radiation. And we would not want that, right? At least not in large amounts, not without huge amounts of shielding. So this one right here works a little bit better. Take deuterium, take tritium, add them together, spit out a neutron and make helium, but it's not active yet. It's not something that scientists have figured out. I like this slide, though. This kind of explains how nuclear fission works, though. Nuclear fission is the neutron plus the 235 becomes a new 36. Splits into two pieces. We don't actually know what those two pieces will be because there's two possibilities, and it'll spit out some neutrons. So that's the basics. I need you to know more or less how fission versus fusion works. So I have a chart here that more or less breaks up into the highlights. This is likely to be something you'd be assessed on. It's just the basics as to what's going on. You're not nuclear physicists. You're not supposed to have it all figured out. So here's the basic ones. Fission involves breaking something up. Fusion involves combining them. Fission involves chain reactions. Fusion does not. You need to bombard something with neutrons here. Fission requires extremely high temperatures. We have the ability to control fission. We do not have the ability to control fusion. Fission involves a whole bunch of nuclear waste, which is actually a huge environmental problem. There's no nuclear waste in fusion because it makes helium. No big deal. You breathe it in, your voice goes squeaky. So what, right? Raw material is actually not very easy to get a hold of because you need uranium or plutonium. Those are not plentiful. You need to enrich it. So fission is not easy to do. Raw material is comparatively cheap and easy to find because all you need to do this is find some hydrogen. You just got to find the hydrogens that are the special ones. Not hydrogen 1-1. You need hydrogen 2-1 and 3-1. But we can find that. That makes sense? Last couple thoughts. I've already discussed this. The two most common uses then of nuclear materials. One is the atomic warhead. I need you guys to be aware that the equations I've shown you are not the only fission and fusion reactions possible. Here's another one. There are atomic warheads that are trying to undergo, we wouldn't call this a hydrogen bomb because it's not actually hydrogen, but this is fusion. Well, actually, no, this really isn't fusion. But this would be, I guess, in a way, a fancy sort of fission, where we could actually take lithium-6-3, hit it with a neutron, and break it up into helium-4-2 and hydrogen 3-1. And so this could be something that you might use in a warhead. So there are many different types of fission and fusion. Don't assume that it's just plutonium, uranium, or hydrogen, helium. So this would have to be fission then, wouldn't it? Right? Where this got split into two pieces. Here is a map that I found. It's probably a few years old by now because I made this. Yeah, I guess this would be 2013. This is a map of all of the countries in the world that have nuclear warheads. And it's kind of crazy to know how many warheads they had at the time. The United States and Russia had like 8,000 nuclear bombs. One would probably be enough, but they have 8,000. So you probably heard about disarmament treaties in your social studies class where they're trying to get rid of needing to have so many because it's insane how many they have. The more interesting thing is how new countries like Israel, North Korea, Iran has been really big in the news recently. Barack Obama and Donald Trump have had different foreign policy regarding allowing Iran to work with different nuclear materials in terms of what they've been allowing, or what they've been allowing doesn't seem like the right word, but what they've been, I don't know, what the global community has been allowing, I guess. And so new countries are starting to gain nuclear technology. The last couple slides I've got on here, just to like show the scope of things. I can't believe this can be true, but maybe it is. This is apparently all sorts of different nuclear facilities found in the United States. Some of these are nuclear power plants. Some of these are nuclear weapons. I just recently drove into Montana. There's apparently a nuke just buried in a field somewhere in Montana, ready to be launched in case of nuclear war. That is slightly terrifying. Anyways. Last slide. This is a basic timeline of nuclear technology over the last little while. It starts here with Little Boy and Fat Man that were dropped in Hiroshima and Nagasaki. And this obviously runs out in 2009. But like I said, this is where physics and social studies, they intertwine. I think it's cool. I mean, I don't ever want a nuclear warhead to go off, but like I like that the physics and social studies have a little bit of overlap. So I like to show you this information. Don't memorize it. You're not going to be asked it. But there is a lot of, yeah, this is what modern physicists want to work on. So, okay, let me do a quick summary, and then I think it's getting close to takeoff time. Stuff that you need to know. You need to know fission versus fusion. Okay, you definitely need to know that. You should be able to look at a chemical equation and recognize what's happening. A really common question actually would be something like this. They might give you a random material, like say 92 over 36. They might give you another random material, 1 over 0. They might say that it now turns into 45 over 12, and they might ask you, what will this be? Do you feel like you can answer a question like this? All you got to do is just some basic math. 92 plus 1 over 0. What is 1 over 0? A neutron, yeah. So 92 plus 1 over 0 means you have 93 total subatomic particles. If this guy has 45 of them, then that would mean that, do some math in your head here, Chris, 48 would be the leftover. And then the bottom number is how many protons you have. So if you had 36 protons and added no further protons, if 12 of them are here, then there must be 24 down there. You'll be given a periodic table. They might ask you, what is this? So if I were to ask you, what is the thing that has 24 protons, you'd have to look at your periodic table and tell me that it's chromium? 19, 20, 21, 22, 23, 24. Chromium, I guess. So apparently this is chromium. Able to kind of follow that logic? So if they give you some random equations here, where they don't tell you exactly what's going on, you need to be able to add your top numbers, which is the mass numbers, and make sure that those add to each other. You need to be able to add your atomic numbers to each other, and make sure those add up. You also might be asked to calculate how much energy is given off. And so you'd find the mass of this and the mass of this, add up those masses. You'd find the masses of these ones here, add them up. They will not be equal to each other because the missing mass goes into the formula E equals mc squared. Those are the two most common things you're going to be asked to do, is just read an equation and figure out how much energy is given off. Other than that, just know the basics of fission and fusion. Questions? You're good? Cool. Okay. We have one last lesson. We're going to do it tomorrow. It's another one of my favorites. We're going to talk about, again, what current physicists are working on. One is the concept of antimatter, which is, it sounds like science fiction, but it's pretty cool. The other one is quarks, which basically describes, well, what is an electron made of? And what is that made of? And what is that made of? And we're going to kind of keep getting smaller and smaller and smaller until we can't go any smaller anymore. So, and that's our last lesson. So if I can give a quick summary of what we're up to. If you guys can see the board over there, today we did fission fusion. Tomorrow we're going to do antimatter and quarks. Tomorrow's the 29th. As of tomorrow, guys, give me one more minute, okay? As of tomorrow, we're done doing content, which is great. Your diploma is on June 27th, I believe. We finished the year on May 29th. I think that's awesome because it means we have a solid month to study. Okay. We're going to do a practice quiz on Thursday, a unit test on Monday, and then we have a ton of time to do a review. Okay. In that time, can you please finish up some outstanding tasks that maybe you realize you were procrastinating on? If you want to redo anything, I'll let you redo anything. And that's kind of our next couple of weeks. I'd like to do some practice finals that last week of school. I'd like you to count 2 out of 4 of them. I'd like it to be worth 15% of what I give you for a mark. That's relatively a small amount, especially if you have the ability to have 100% going into that. It'll change your mark a little bit, I'm sure, but I don't think it's catastrophic. I think it's only fair, though, because my first semester class did it as well. So, okay. Does that work? You guys, no questions? Okay, I'm done. You guys can take off. Thanks, everybody.